Welcome back to the lectures on high-performance scientific computing. In the last few classes, we have been discussing a little bit about computer architectures, especially how large parallel machines are organized. We're looking at a little bit of the internal structure of those architectures, and so to give you an idea about how we need to go ahead programming them. In today's class, we're going to look at very specific architectures which come out from the company Nvidia, and these are related to GPGPUs. We discussed a lot about GPGPU computing in the previous lecture as well. The slides today are provided by Nvidia. So the first thing that we need to ask is, what are the emerging grand challenge applications when we are trying to use computational models? This obviously spans a lot of fields, from Earth systems modeling, looking at complex climate models at the full global scale, looking at weather models at both the global and the local scale. Usually these models take a really long time to run. We are trying to predict the weather for the next few days or few weeks, and in terms of climate, we are trying to predict the climate for the next few decades. Similarly, we try to model very complicated stuffs in biological systems like the human microbiome modeling. We have complex engineering systems like aircrafts, power plants, so on and so forth. We would like to do environmental modeling like the distribution of microplastics or distribution of aerosol in the environment. When we try to do inverse problems like material design and novel drug design, these are very large system models. The challenges that are faced by all these applications is that they all span several orders of magnitude in space and in time scales. For example, if I were to think about a power plant, a power plant is very large in terms of geometric space. But the phenomena that takes place, if you think about it, goes down to the combustion which is happening at a micro scale. The time scale at which this also occurs is pretty significant. Typically, combustion is taking place in a few microseconds, whereas a power plant is continuously operating on the scale of days, if not weeks. They also span a large number of phenomena, like there is chemistry involved, there are physical systems, and it also may involve quantum systems if you're trying to model quantum computing. A good example is, how does aerosols affect ocean circulation? The ocean is pretty large, spans several thousand kilometers in scale, whereas aerosols are particles of micrometer size. But it is well known that the emission of aerosols and the transmission of aerosols affects the circulation of ocean, which in turn affects a lot of other physics in the ocean. There is a challenge here when we are trying to do these computations. We have challenges in the silicon process technologies which are cramming more and more transistors in lesser and lesser space, but eventually this has to break. Many algorithms might not be sufficient or even possible to be solved on this sort of hardware. Now, typically in the past, we would scale our problems over distributed machines by using legacy codes, using something like Fortran or C, combining it with MPI over distributed machines. Also, there's a clear distinction between what is a CPU and a GPU nowadays. In the future, such homogeneous CPU nodes and GPU nodes may not be sufficient. We might need to have combinations of both. There's also a large growth in machine learning and deep learning, especially if you look at data-driven algorithms. So when you look at these simulation technologies, when you combine the power of machine learning and the availability of data, we can then really enhance our understanding. So if you really think about it, machine learning is very rapidly becoming the fourth pillar of scientific discovery. So we can look at approximations, we can look at inverse problems, we can look at insights, empirical insights from experimental data. So for example, the protein structure prediction has become a solved problem. So the other thing that we would like to look at is forecasts, weather forecasts, especially in subseasons. In computational fluid dynamics, physics-informed neural networks is becoming a big thing. All of this have significant amounts of data in common. What artificial intelligence has done is that it has introduced a new case for science and engineering. It tries to bridge the gap between simulation and real time. If we were to look at an axis or a graph of the computational cost versus the error in your simulation, if you want the computation to be done in order n time, the error is significantly large. As we increase the computational complexity towards n square or n cube, the computational costs increase in logarithmic fashion. And as we try to approach the exact solution, it becomes almost exponential in n and prohibitively expensive. We try to do AI surrogate modeling at a fraction of the computational cost, but then we try to significantly reduce the error. So this is where data-driven simulation gives us the advantage, where we can drive the error low for a fraction of the computational cost. For example, here there's an example of data-driven weather models, and there is a comparison of the resolutions of this data-driven weather models since 2018 in a publication by Dubin and Boyer. So what essentially we are trying to say is that if you want to do a full weather model for the entire globe, it's much easier to do it with data-driven technologies using AI and ML from a computational perspective. Similarly, there is a case for doing digital twins, especially for science. For example, if we have a physical system which has sensors, cameras, and different sort of instrumentation, which is capturing some sort of experimental data, that requires a lot of money. It also requires human beings to run these experiments. We can then create a twin, a digital twin for this in the virtual world. So where data is being harvested from existing physical systems and then sort of being interpolated using AI as a surrogate. Here we use conventional physics models as well. So if you're able to build a full stack digital twin of any process, for example a power plant, then it is very useful to do simulations. So what are the emerging challenges again? We need to have supercomputers which may need to integrate with sensor networks. Supercomputers are very data hungry. It needs to have very high throughput from scientific instruments. The data collection, data logging needs to be fast enough to feed these supercomputers. And more importantly, the high performance computing and machine learning should be run in some sort of a tightly coupled loop. So if you really look at it, what are the workloads of a modern supercomputer? You have simulation plus AI, you have edge computing, you have actual simulation, you have digital twin, and then finally we are trying to do some sort of quantum computing as well. Well, today a quantum computer is realized, but a large amount of the quantum algorithms are now emulated on modern supercomputers for testing for future quantum machines which will be built. For this, we need to have supercomputers which are then networked to the edge, which is getting all the data, which need to be connected to the cloud to push the data, and then you need to have some sort of extreme input-output. But what does Moore's law tell us? Our performance is sort of plateauing. While the transistor density doubles, power stays the same, cost stays the same, Dennard scaling has hit its limit. So the cost for computing is increasing at the microprocessor level. Also, one of the challenges is to move data quickly. The other big thing that happens is how much energy is being consumed by memory, and especially moving of data. So this chart tells you with the change in voltage how many joules is required for doing certain operations. You can see clearly that movement of data and memory clearly dominates the energy consumption. So what is the philosophy that one of the manufacturers, Nvidia, has taken? They are trying to do end-to-end mapping of applications to supercomputing systems. They're trying to improve the algorithms, the software and the architecture, and trying to aim at almost 6x generation to generation performance improvement. Obviously, this requires a close collaboration with all HPC scientists, machine learners, and deep learning community. So what we are really trying to look at is how the memory is moved and what is the best floating point operation per second one can achieve. To that end, we will now discuss the future upcoming Grace ARM CPU. Let us now see how is the ARM CPU constructed. ARM stands for Advanced RISC Machine, which is a 64-bit server class computing core, and it is also a system on chip. It supports all vector extensions and neon instructions. It supports 48-bit virtual and 48-bit physical address space. And it gives you a balanced architecture between single core performance, core counts, memory, and the I/O systems. This CPU is ready to boot any sort of Linux operating system, and most of the HPC stacks will run straight out of the box. It does not require any special tweaking. On the scalar side, you can do wide superscalar operations to get very high single-threaded performance. It has a 64-byte cache line, a 64 kilobit L1 cache, 1 MB private L2 cache. If I go onto the vector side, it supports 4 128-bit SVE2 execution pipes, which is capable of doing 16 double precision floating point operations per cycle. It supports 64-bit, 32-bit, 16-bit, and integer 8 operations. It supports complex data types and mathematics. It enables easier vectorization. It allows the lane widening and narrowing of instructions. It has classic and non-temporal gather, load, and scatter instructions. It also has instructions for crypto. So this is essentially a processor which is designed as a system on chip. It has up to 117 megabytes of shared L3 cache, and it can do data transfers up to 3 terabytes per second on die. It has an extensive set of core and uncore performance counters. It has thermal monitoring, power management. It allows for individual core power and clock gating. It allows for virtualization, has support for security. It also has logic support for direct communication between GPUs using GPU Direct and CPU-GPU movement and synchronization. So in a high performance world, you have the Nvidia Grace CPU architecture, which has 144 CPU cores, and it has a bandwidth of 1 terabyte per second with the DDR5 error correction code RAM. It has almost 3.2 terabytes per second of cross-sectional bandwidth. So it's essentially a superchip. It can combine itself with the Hopper GPU, which we will discuss in a minute. And if the CPU and GPU are combined together, it has a 900 gigabyte per second coherent interface, and it can do up to 70 teraflops of FP64 calculations. It can do 2 petaflops of half precision AI calculations, and it has 600 gigabytes of memory. The best part about this processor is that the entire Nvidia ARM HPC software ecosystem is available for it. So all the HPC software development kit, the compilers NVC++, NVC++, NVC, NVFortran, NVCC are available. The core C++ libraries which are used for programming are available. You have profiling tools. You have the communication libraries for the MPI stack. You have other libraries for data analytics and AI available as well, and traditional math libraries such as cuBLAS, cuFFT, cuTensor, so on and so forth are available. And all of this will be able to run on Nvidia hardware directly. Let us now look at the Hopper GPU. So the Hopper is a new symmetric multiprocessor which improves raw speeds and feeds. It has ideas like new thread block clusters which turn locality into efficiency. We will discuss these advanced topics in future lectures of GPU. It also supports distributed shared memory between symmetric multiprocessors. It has a new tensor memory accelerator and supports fully asynchronous data movement. And it has special new instruction sets called DPX and a new transformer engine for AI modeling and acceleration. So thread block clusters is a new feature which has been introduced for programming locality in clusters of symmetric multiprocessors. The advantage of this is that you're going to get 7x times the throughput compared to using global memory. The shared memory blocks of the symmetric multiprocessors are within a GPU. This allows the processing cluster to communicate directly without going to the HBM. The leveraged CUDA cooperative groups are available through an API. Cut this slide out. So if you look at the Grace Hopper combination, this is a new revolutionary architecture. It does latency hiding throughput machines. It basically does asynchronous computational graph solvers. It can basically effectively map data flow complex portions of the algorithms. It also has custom IP blocks for energy efficiency. So the Nvidia CPUs are superscalar, are tightly coupled SoCs with balance bytes per second and floating point operations. It has the ability for doing strong vector and tensor performance. The entire thing is manufactured on a unified compute substrate. This is how the machine looks when it is held in the hand. So if you were to look at an arrangement where you couple several of these, here is a small cluster of 36 Grace CPUs, which are then interconnected using one NVLink. These are connected in the all-to-all format and is capable of delivering 130 terabytes per second bandwidth. So what is the accelerated computing platform used for? It can be used for data processing. It can be used for advanced CAD, computer-aided engineering. It can be used for computer-aided drug design, climate simulation, quantum simulations, robotics and industrial digital twins, and obviously enterprise AI. All of these are supported by the CUDA extension libraries. And this run on the accelerated computing platform, which is the Grace Hopper platform. So if you look at it, if you look at a computational graph problem and you try to use it on the Grace Hopper, you need to use the same programming model for CPU and GPU. So all your existing applications will be able to run immediately on this machine. This has true unified memory and high bandwidth link, so this makes data movement less of a bottleneck. Existing CPU programming models will continue to work on Grace CPU with much higher performance. The senders and receivers enable defining hybrid execution graphs to take advantage of the strengths of each of the processors. Being on a unified compute substrate, the Grace plus Hopper enables a broader set of all codes to be accelerated. The Grace plus Hopper architecture enables mapping of both control and data flow complex portions of the algorithm efficiently. It enables a mapping of multi-scale, multi-physics applications, post-foundation, artificial intelligence, and complex workflows. The standards-based parallelism enables productive portability amongst different platforms, especially if you are trying to take the same code to other different types of machines. Even if you have non-accelerated or fully accelerated or mixed control flow data flow applications, this can be run on Grace Hopper. Mapping of these complex workflows on distributed heterogeneous compute platforms requires things like Omniverse and digital twin frameworks. The other good advantage of these superchips is that they save energy. So if you look at the model, you have the x86 CPU typically, which is attached to the Hopper GPU using some PCI Express bus. This is the traditional way of doing calculations. Here, if you want to transfer data between the CPU to the GPU, it typically costs about 6.5 picojoules per bit. If you want to transfer data from the CPU to the main system memory, it costs about 35 picojoules per bit. Typically, the cost of doing a floating point operation, a double precision floating point operation on the CPU is 99 picojoules. On the Hopper CPU, the same cost is about 12 picojoules per floating point operation on double. Now, if I have a unified super chip, which is a system on chip, the transfer of data between the CPU and GPU costs only 1.3 picojoules per bit. This is almost 5 times less than the conventional method. Similarly, it costs 7 times less at about 5 picojoules per bit to transfer data from the CPU to the system memory. And the cost of doing a floating point operation is about 62 picojoules on the Grace CPU, and it remains the same as 12 picojoules on the Hopper GPU. So clearly, today's applications involve a lot of data transfer between the CPU, the GPU, and the memory. So if you have a unified chip like this, you can see the 7x reduction of data transfer between the system memory and the CPU, and the 5x reduction of data transfer between the CPU and GPU is going to give us enormous benefit in saving energy. The other advantage of using something like this is that you could do co-scheduling. If you have multiple jobs which are to be run on the same CPU, GPU combination. You can have obviously one job which takes up the whole node, which takes the CPU and the GPU completely, or you could divide it into several jobs. For example, job A could use 64 Grace CPUs, job B could use 8 Grace cores and then the Hopper GPU. So you have one job which is capable of running only CPU and the other job which is running on the CPU GPU combined. You can also have two jobs which are using both the CPU and GPU. So for example, you can use 8 CPU cores and see part of the Hopper GPU as one GPU, and you could have several jobs running at the same time, which can do MPI plus parallel GPU computing or OpenMP and parallel GPU computing. So what essentially this does is that the combination of Grace and Hopper makes acceleration more accessible. So if you look at the normalized execution time of different applications, if I were to run it only on pure x86 and let us say I normalize it to 1, if I use it x86 plus the Hopper GPU architecture, it typically will run about 1.16 times faster. If I do it on the Grace Hopper platform, it almost runs 4.25 times faster. We are also able to move the descriptive parallel expression using standardized ISO language parallelism to these platforms. We can do the parallel expression as a computational graph. We can decouple the scheduling from the expression of the algorithm, and we can take the operating system runtime to provide hardware capabilities as hints to the scheduler. So this will definitely accelerate the computing. Thank you.